Hello, today we'll be talking about attacks on control flow. This is the 10th lecture in the ECE 209 AS winter course. My name is Luis Garcia. I'll be your guest lecturer for today. I am a postdoc in the Network and Embedded Systems Lab working with Dr. Mani Srivastava. And before we get started, I just wanted to make sure that everyone knows we're working with Linux distributions in this lecture. So I highly recommend, for example, downloading the latest version of Ubuntu, and then you could use a hypervisor like VirtualBox to run this operating system in case you have Windows or Mac, for example. Okay, back to the lecture. And before we get into control flow attacks, I first want to talk about the two general security models that are considered when crafting these control flow attacks. The first being capability-based security mechanisms. And these are typically communicable, unforgeable tokens of authority that where their values are reference an object associated with a set of access rights. So for example, the etc password file, this is available in all Linux systems usually, and it has information about all the users in the system, and it's readable by all users in the system, and it'll tell you, for example, what group they belong to. So it tells you what communication can be done between these users and what files they have access to. So here, if we output the contents of this file, you can see it has the name and, for example, the default shell associated with it. The reason why it's called the etc password file is that it actually used to store the encrypted hash of the passwords, but because it's accessible by all the users in the system, they decided that that's relatively easy to hack. So they actually moved it to the etc shadow file. So the shadow file is now only viewable by a single user, or whichever users have access to it. But you see, actually you have to be a super user to actually access this file. So if we actually show here, we do a super user access to it. So these are actually the second value corresponds to the password, and these symbols correspond to, okay, maybe the exclamation point corresponds to the password not being set for a particular account, and so it's locked. And the asterisk, for example, shows something that shouldn't necessarily be logged into, or so. There's a whole structure to this, but the point is that this is a capability-based system, in that it provides a mechanism for everyone to see who has access to what. And a more familiar example would be the read-write permissions that you provide a program when you want to manage what access rights it has to a particular file. So for example, this read-write would be to say that a program could read and write a particular file. And operating systems with these capability-based security mechanisms were designed so that user programs can directly share capabilities with each other. This is the principle of least privilege, where you only want to provide access to privileges when necessary. And you could also think of, Android or smartphone permission systems. And the operating systems provide this infrastructure to make these transactions efficient and secure. And some recent examples of these operating systems are the L4 microkernels and the Google Fuchsia, which we won't get into in this lecture. And the second type of security model that I want to discuss was the hierarchical protection domains, or the protection rings. These typically consist of two or more hierarchical levels or layers of privilege within an architecture, and they're generally enforced by hardware or microcode. So Intel x86 processors introduced protected mode in 1982 as opposed to real mode, because this enabled virtualization of memory and allowed you to essentially enforce these mechanisms virtually. And it's typically not present in low-end embedded processors that you'll see in CPS and embedded devices. And I'll show you in a bit in the coming slides an example of how these memory layouts might look. And there are usually special gates between these rings for access control. And the notion here is that we want to allow an outer ring so this green ring here, for example, to access any of the inner ring's resources in a predefined manner. And this will be more clear with an example in the next slide. But most general purpose operating systems usually use only two levels, kernel versus user mode. And in x86, commonly Linux and Windows kernels usually only use 0 and 3, and where 0 is a kernel and 3 is for users. And they also, there's this notion that a hypervisor represents this ring -1, because if you're virtualizing an entire operating system, then technically your hypervisor would sit at a layer below in security. So, for example, in Linux, if we wanted to facilitate communication between a user-level program sitting on ring 3 and a kernel-level program sitting on ring 0, we would use what's called system calls. So, for example, if we have our favorite printf function and we're trying to, the way that it would work is it would actually make a call to standard C library, and the standard C library would call write function to standard output within the kernel. So your program makes a library call to an intermediate library that's interfacing with the kernel, and this makes a system call to the Linux kernel. And there's actually a couple useful tools for reverse engineering techniques. If you want to see what library calls and system calls a binary file is doing, that you don't have access to the source code, you could actually use ltrace and strace. So here, for example, if I am outputting the context of, let's say I have test.c that's just printing hello world, and I compile this to some function, to some binary, let's call it test.o, and normally when I run it, it'll just say hello world. But if I use ltrace, I could look at all the libc functions that it's calling. So here, test.o, you see it calls this libc start main, and it calls puts, which is a libc function. And if I use strace, you could actually see, if I use strace, you could actually see that all the kernel level functions that are being called whenever you run a printf. So all this is running whenever you run your simple printf functions. So to actually enforce these mechanisms, most kernels have what's called a trap handler. So in between the user mode and the kernel mode, there's usually a hardware implementation of the boundary. And generally, processors have two modes, either user mode or kernel level mode. And so they'll typically be equipped with some hardware device interrupt, hardware exceptions, software exceptions, virtual address exceptions. And on the user side, you'll have these system service calls. And when a system service call is made, it communicates with the system service dispatcher residing in the kernel that has your system call table. So whenever you create a new system service or system call, you typically have to register it in this call table. And then this is what actually reaches out to the system services. And within the kernel, you also have all your interrupt service routines, your exception dispatchers that have all your exception handlers whenever one of these exceptions happens, as well as the VM manager's pager. So these hardware level protections are useful for providing these security mechanisms, obviously. But what about the bare metal embedded systems that I mentioned that typically don't have these protection mode mechanisms? Normally they will have one slab of shared memory space. And what this implies is that actually if an attacker can find an exploit in any point in the code in any aspect of memory, then that implies that he actually has the ability to read or write to any other component in memory. And in cyber-physical systems, this has severe implications because, for example, if we compromise the web server of a drone, then we may be able to write to the GPIOs in memory that are controlling the rotors of these functions. And this was actually the premise for a paper that I worked on back in 2017 that was presented at NDSS that was a physics-aware rootkit. And to implement this attack, we actually used an exploit to perform a control flow attack, and this essentially causes to subvert the GPIO mechanisms of the system to attack a power grid. So in our paper, we actually attacked a generator, and we were able to spoof measurements that are being reported to the operator while driving the generator to unsafe limits. But this was all enabled because these controllers had one slab of memory space on their microcontroller, and by exploiting one aspect of the firmware, where you're able to write and intercept the communication to the GPIOs. So hopefully that was a good segue into the meat of this presentation, which is the control flow hijacking attacks. And the general goal of these attacks is to take over the victim system. And these systems could range from home gateways to any IoT device, or even a cyber-physical system like a drone or the controllers that I attacked in the Harvey paper. And it essentially allows you to execute arbitrary code by hijacking the application's control flow. And this is enabled by all these bugs that exist in these systems. So there's a whole bunch of approaches such as buffer overflows, integer overflows, format string vulnerabilities, double free, and many more. And we'll get into a few of them in this lecture. But the most common is the buffer overflow bug. And this is ubiquitous in C and C++ programs. So in order to understand where these bugs come from, let's take a step back and look at how programs are loaded in process memory. So if you have your program file that you're trying to load, it typically consists of this program machine code as well as the global data, and this is essentially copied over into the process memory. And right above that, you're going to have the heap, which essentially is all your dynamically allocated variables in your program. So anything that you use, for example, in C++, we call the function new, or in C, you might call malloc to dynamically allocate memory. These variables will be stored in the heap. And then at the top of memory, you're going to have the kernel code and data associated with your memory, and you're also going to, associated with your program. And you're also going to have what's called the stack, and the stack will have all of your stack frames associated with each function call. And these we'll get into the stack in a bit, but these will essentially have all of your function calls and your stack frames that have your local variables and your return addresses and your frame pointers. So, for example, let's say we have two stack frames here where the result of two functions being called. So function P is called, and then function P calls Q eventually. So because the stack grows down, what function P would do is it would first push the return address of where it's going to return to once it finishes, and then it would push the pointer of the previous frame that called P. And then let's say P at this point would call function Q. It would push the two parameters of the function Q onto the stack, and then it would then this is the start of the Q frame where we would essentially push the return address of P here, and it would also similarly push the old frame pointer that pointed to the previous frame, and then it would push any local variables that are declared in this function Q. So here, because this is the end of what's been allocated, this would be where the stack pointer is pointing to, and any other new stack frames or function calls would be placed below Q. And so this is the stack frame in a nutshell, and this will be important for understanding how stack buffer overflows work. So let's make this a little bit more concrete. So on the left, we have our C code that has the main function that's calling a function foo, and the main function stack frame will be in teal, and the foo function will be in yellow. So when, as you can see as before, the main function is first pushed onto the stack, and then it passes these parameters A, B, and C, that are pushed onto the frame, and then foo's frame will start after that. And because we have two locally declared buffers, these will be placed at the top of the frame here. So that's just a very simple example as to how this, how two function stack frames would look like in sequence. And I'm going to quickly digress into a very brief x86 tutorial for those of you who are a little bit rusty with your x86 assembly. These are instructions that I'm going to be referring to in the coming slides, and they're very common in terms of seeing what happens when you're generating these stack frames with your code. So, for example, push EBP just pushes your base pointer onto the stack. Your base pointer is going to point out where your code starts, and at the beginning, your stack pointer is typically pointing to the base pointer, and your stack pointer grows down. So when you start adding buffers to your stack, the stack pointer is going to continue going down, and that base pointer is there to provide you with that address whenever you need to calculate any relative offset addresses, or you need to know where your code starts and or where your variables are going to be, like all the parameters that were passed to the function, for example. And then here's this instruction that's moving the ASP into the EBP value. Here, this is subtracting 4 from the stack pointer. So again, when we push a variable, for example, 4 bytes onto the stack, you're going to be moving that stack pointer down. And this is just showing you how you might call a function that's at this address, at this hex address. And this function here is essentially subtracting the base pointer by 4, and this is what happens when when we're moving it, when we're adding a new stack frame. And this instruction here is actually loading the address of a memory location pointed to at EBP -4, so that might be some variable, into EAX, which is one of your general purpose data registers. So this might be, before you're doing some manipulation or, performing some arithmetic operation. And your ret is just your return. It jumps to the return address that's saved on your current stack frame. And finally, the no-up is just a no operation. So it essentially does nothing, but we'll see why those are important in a few slides. So revisiting the previous example, we're going to see how these assembly instructions actually look like. So with this main function, at the top, we would have the base pointer, and we would have the stack pointer pointing to the end of its space. And what it would do is essentially call these push functions, where you're pushing the parameters of the foo function, CBA in reverse order, and then you would push the return address, and then the new base pointer would be placed where the code for foo would start. And you can see that the base pointer would be done by essentially pointing the base pointer by moving the stack pointer value into the base pointer. And now we can start our code, and here we would, because we're pushing multiple variables or whatever we're pushing onto the stack, we would then move the stack pointer to its new location. So a stack buffer overflow occurs when there's a buffer located on the stack, as was shown in our previous example. And this was used, the first popular example was the Morse internet worm that happened in 1988. And the smashing the stack paper popularized it, and you could read that paper if you have spare time. But essentially, if you have local variables below the save frame pointer and return address, an overflow of a local buffer can potentially overwrite these control items. So this is not only can you overwrite, for example, if you have two buffers in sequence, not only can you overwrite another buffer's data, but you can also overwrite the return address to branch to some desired code. And we'll see how this can play out. And this is an example of a control flow attack. So let's take a look at a simple example of a stack buffer overflow. On the left we have some vulnerable code, and on the right we have the associated stack. And the main function here takes in an argument from command line and passes it to the function foo. And the function foo will essentially copy that that argument to some local buffer here. So if we, for example, were to call this function, and let's say it's called, let's say we pass the word hello, so I believe I have the function already compiled here, so I think it's buffer overflow simple, and let's say we pass it the function hello, it will just, it won't do anything, it will just copy hello into this buffer. But now what happens when we override it with a very large buffer. Let's say the input is a bunch of A's, and then we actually put in the little endian value of an address. What this will do is actually overwrite the return address of this stack, and then have the function branch to some arbitrary code or whatever function is at this particular address. But if you'll see, actually, in modern operating systems, if you just, let's say we, make a very large buffer that's larger than 12, because the buffer here is only 12 characters, it will actually detect that smack stashing is happening. So modern day operating systems typically have protections, but we'll see in a bit how we can disable it to test some of these techniques. And it doesn't necessarily have to be malicious. A lot of times you will have benign buffer overflows. I'm sure several of you have accidentally created buffer overflows when you've been programming. So this program will cause a seg fault. So I've compiled this into this function called benign overflow, and when we run it, the same thing will happen. It will detect stack smashing. So let's take a look at what's happening here. It's declaring some large buffer, about 256 characters, and then some integer I, and then it's filling the entire buffer with 256, and then calling some function here that essentially does the same thing. Here it is taking in a string and it is copying it to a local buffer. In this case, it will try to copy, because stir copy itself is a vulnerable function. It doesn't check to see if both buffers are of the same length, or at least if the destination buffer is bigger than the source destination, the source buffer. So in this case, it's trying to copy a 256 character long string into a 16 character buffer. And of course, if the buffer's here, it's going to overwrite all these other components in our stack. So taking a deeper dive in as to how this works, let's say we have this function as before, where you're taking in an input buffer and you're copying it to some local buffer. So what function would look like on the stack is the same as before. And what happens when string is 136 byte longs? So after the stir copy call, we would actually overwrite both not only the stack frame pointer, but also the return address. And this is, as I mentioned before, because stir copy doesn't have this checker for the length of the stir argument. So what can we do with this? So let's say now the attacker actually created some larger buffer where the input string was actually, it not only overwrote the return address, but it included some extra buffer at the top that included some program P. So they overwrote the return address such that when this function exits, it would actually return into some code here. And what happens, let's say if program P had the string exec/bin/sh, what would actually happen is that the user would get a shell. The attacker would be able to get a shell, and this is called a reverse shell. And normally this implies that the code P would run on the stack. And nowadays, operating systems do have these protection mechanisms to void to create a non-executable stack, which I'll discuss in a few slides. So how does this attacker determine where to return in this program P? Because it's usually when your program's loaded, the memory might be a little bit non-deterministic. So what they do is they have actually a no-op slide. So essentially what you do is you will, in your buffer, just write a whole bunch of no-op operations, and that way you can essentially put your program P inside this very long list of no-ops, so that you just have to have a vague notion of what the return address will be, and you can jump into this no-op slide, and then because the instructions are executing this way, it will execute program P. So you don't need to know an exact address as to where program P is, you just need to land somewhere in your no-op slide. So there are several methods of crafting payload code, and for example, you would want to first generate the assembly code. And what I found is it's actually better to just write the payload in assembly, because when you use it, let's say you write some code that you want to execute in the stack, if you use a off-the-shelf compiler, it may introduce some optimizations that will cause just confusion of what you're trying to do, and normally what you're trying to do could be expressed in much simpler assembly code instructions, or you could just generate the associated binary instructions. But in any case, what's important is that you want to make sure that the Indian order is correct for the hex values of your binary instructions. And so, for example, let's say we want to write an exploit program. We could actually write this in assembly as follows. This is equivalent to this code, and you could figure this out by using a simplified compiler. But to actually execute this code, we're going to have to do some modifications, and it will end up looking like this. And this is because there are some basic requirements when you're generating these payloads. So for example, we want to make sure that the /bin/sh is null terminated in memory. So we want to make sure that when you pass it to the execv argument, that it has that string terminating null value. So there's a way you can do this by having essentially following these instructions, where you have an address of the string in memory followed by a null long word, and you copy 0xb into EAX, and then you copy the address of the string into EBX, followed by copying the address of the string into ECX, and you copy the address of the null long word into EDX. And this is all done in this sequence here. And then finally, you want to execute int80, which is essentially executing a system call. So let's say we have this simplified payload that we've just created based on what we just mentioned, and now we want to actually inject this payload into a buffer. So how would we know where to actually have this code execute? So we previously mentioned that you could generate a no-op slide so that your code can return to this address in a slide of no-ops. But as we'll discuss in a bit, sometimes the address space could be randomized, and predicting where the no-op slide will be could be tricky. A simpler approach could be to use relative addressing, where you would essentially calculate how many bytes each of your instructions will be in your payload, and use relative addressing when it comes to, for example, your jumps and all, and your return addresses. So here's a hex representation of our payload and how it would look like. So you would have this shell code, and then this would be your payload code that you would generate and you would want to have executed. And you could use, let's say when you generate your code, you could use any disassembler such as GDB to create this. So for example, if I had some binary called test.o, we had previously created a test.o. I could use object dump, which is a object object, if I could type correctly, object dump dash D, which is the disassemble option, and test.o. So imagine that we had compiled our previous code, so you can compile, using gcc-c assembly code into a binary code. Then here I could disassemble this, and not only can you see the instructions on the right in assembly, but on the left you have the associated hex representation that you would use to generate this shell code here, to create this attack buffer. And this is just an example of a stack smashing attack where you would be able to implement, where you would actually be able to generate this shell code. And we'll show a live demo in a bit. And this is another example of how the shell code would look. I just wanted to highlight here that if we did indeed use a no-op sled, this would how it would look like at the end of a no-op sled. And you could take a look at this code in detail, and when I show you later how to disable the stack smashing mechanism, we'll see how these attacks actually look like. So stir copy is not the only opportunity to actually exploit these. So there are several unsafe functions in libc itself. So stircat, gets, scanf, and several more. A lot of these string functions don't do the proper vetting of the strings that are passed to them. And then, but there are practical issues with actually implementing these payloads that need to be accounted for. So in addition to some of the limitations I mentioned before, you also want to make sure that, for example, program P or your payload doesn't contain any /0 character. So you don't want the string to be null terminated early before it, for example, executes your exec bin/sh. And the overflow should also not crash the program before the function exits. So you want to make sure that you maintain the integrity of the core structure, and you know where to write the correct return addresses and so on. And you want to be returning to valid addresses. And also finding the buffer overflows is actually difficult. So one way you can do this is, if you do have the code, you can run the code on your local machine, and because you're not going to be, for example, if it's a web server, they would obviously be trying to detect if somebody is trying to perform these types of attacks. But if you run it on your local machine, you could, for example, issue some malform requests that end in, for example, a bunch of $signs. That way, when you look at the output, you could see if any other components in the memory are being overridden. And also there's automated fuzzing techniques that actually, such as tools such as Metasploit, that actually take care of a lot of these techniques and perform this for you. And if the code crashes, for example, you can search the core dump for your injected malform request to find the overflow location. And the challenges are increasing due to these modern defenses. We've mentioned a few of them, such as the stack execution protection, and we'll discuss a few more defenses that have come about since the advent of these control flow attacks. And there are other opportunities for buffer overflows. So for example, you can overwrite the address of exception handlers that are stored on the stack frame. More practically and more commonly, programmers do tend to store function pointers on the stack as well. So for example, if we were to do a object dump of our previous any one of our previous programs, you can see these are some of the addresses of some of the functions here that are coming up, and you could, so essentially the function pointers will be stored dynamically, but with each function there is an address associated with it that you could exploit. And also, long jump long jump buffers can be exploited as well. So if you overflow the buffer next to the position that you're trying to do a long jump to, you could overwrite that value as well. And this was a vulnerability in Perl version 5.003. And you could also corrupt method pointers as well. So when you have a compiler that compiles some C++ code, it will generate some function pointers. So for example, here we have some object T that has some data, but it also has some pointer that points to some V table that stores all of its associated functions. So if we have some buffer, then in this data, then we could overflow this V table, and we could overflow the pointers that are pointing to it. So this is an example of how we could actually exploit the object-oriented structure of C++, where you have these method pointers being stored in these objects. And so within the members of a particular class, you could overflow a particular buffer and then override the associated function members. So this is just an example of how you can implement this, let's say by using a no-op slide that leads to some shellcode. And another type of attack are integer overflows. And you could actually see, if you guys want, you could check out this blog entry from Frack. So Frack is actually a hacker blog made for hackers, and they have, they have a breakdown of what basic integer overflows are, but also they have some nice real-world examples that you could read. And in general, this is a good reference for different types of hacks and some 0 days that have come out. So it's something to keep in mind if this area interests you. And so let's take a look at some of the basic data structures in these programming languages. So an integer is 32 bits, a short is 16 bits, and a char is 8 bits. So these are not very large values. And what happens when any one of these data structures exceeds its max possible value? So if a char is 8 bits, the max value is 255. So for example, if we were to add these two hex values, which would be 128 plus 128, the result would actually be a char overflow, which would mean C is reset to 0. And same thing would happen for shorts as well as integers. So how might an attacker exploit this? So let's say we have this function here that was written by some programmer that thought they were familiar with buffer overflow attacks. And this function is just simply trying to concatenate the second buffer to buffer 1. So to combat buffer overflow attacks, they implemented this length check that says, okay, we have this small local buffer here, and we want to make sure that the length of buffer 1 plus the length of buffer 2 doesn't exceed the 256. So if it's less than 256, then it would essentially copy buffer 1 into the beginning of the buffer, and then copy buffer 2 at the end of buffer 1, and then it would just do some stuff. Now, what happens if the length of this buffer is equal to 0x80, and length 2 is equal to this very large number? Then what will happen is that they will have an integer overflow, and it will actually cause the second mem copy will provide an overflow heap, and this will allow the attacker to circumvent this quote-unquote buffer overflow check that they've implemented. So the buffer overflow attacks aren't the only way to implement a control flow attack. There's another class of attack called the format string attacks, where they target incorrect usage of format string functions. So let's take this example on the left where you have a function that's taking in a string and feeding it into the fprintf function as following. So what happens if this buffer that's passed to this function is actually a format string in itself? And normally when you pass a format string, you would expect an argument after the format string. So most likely this will cause a program to crash, which is in itself a form of denial of service. But if not, if no critical component of the code is overridden, then you could actually print memory contents. And this could lead to privacy issues. For example, if you have some secrets hidden in your code that you don't want to leak out to standard output. And as we'll see, there's actually other ways in which not only could you read the contents, but if you use this format character %n, you could actually write to the contents as well. And there's a whole suite of these vulnerable functions, which essentially is any function that uses a format string. So, for example, printf, fprintf, sprintf, and so on, as well as any of the logging functions that are built into a lot of the libc libraries. So here's an example of a format string problem where we have a printf that's taking in an argument from the user and then just printing some value after. So if, for example, we compile this to some binary program called format error and we generate we pass it hello world, then it'll just print out hello world. And if we say something like go Navy, it'll print out go Navy. But if we pass it this %x, it's going to print out the hex of whatever the argument is after this. So in this case, it prints out some address here, which most likely corresponds to the hex values associated with this function called here. And the problem becomes more interesting when you find some of the more obsolete format characters that are still viable. So in this case, the %n is a format character that will tell you how many bytes have been written up until the point that you print. So in this case, it would count how many number of bytes have been written in the string up to here, and then store it in the associated variable here. So in this case, the number of bytes written up to this point will be written in count 1, and the number of bytes written up to the second point here will be written in count 2. But you can see how if you don't have any variables being or arguments being passed to this printf function, then it'll write to the value, the address space that happens immediately after this call. And to kind of break it down a little bit more, you could see this is how the stack would look like. So if we call this printf here with some format string and the associated arguments, you'll see that the format string resides here, and the arguments would reside here, followed by the local variables and the return address and so on as before. Now, if we remove the arguments, the format string will be adjacent to the local variables and all these other components. And you can imagine that if we remove these arguments, it's going to be looking, it will essentially apply them to this. And what that, in summary, you can either use this to dump arbitrary memory up the stack, where you crawl up the stack until you find some desired pointer, or using the %n, you could write to arbitrary memory. So for example, here you would write 6 into temp, but if you have this, if you first walk up the stack, then you could write to some value to some arbitrary memory point. So now that we've discussed a majority of the attacks, how do we go about defending against these attacks? And there's a broad category of approaches. The first being detection. So for example, can we actually detect that there is a stack overflow and prevent the redirection of the instruction pointer to some malicious code? The second would be preventing these types of attacks. So first would be, either using type-safe languages or using a tool that verifies you're not using any vulnerabilities, but also preventing execution of malicious code from the stack without directly detecting the stack buffer overflow. And the third and more commonly approached is randomization of the memory space, such that even if you could implement a buffer overflow or any of these attacks, then it would be difficult to use either create some executable code in your payload or use some other form of attack. And there are several examples that we'll discuss in the subsequent slides, such as stack canaries, non-executable stack, randomization of the stack, runtime libraries, and so on. But we'll cover these in a bit. So the first of these approaches is making the memory non-executable. And to do this, you can essentially prevent attack code execution by marking the stack and heap as non-executable. And what essentially they've done is implemented this NX bit in the page table entry that signifies whether this code can be executable or not. And it's typically available on all major operating systems such as Linux and Windows, which calls it data executive prevention, OSC, and so on. However, embedded systems often don't have this virtual memory, but code memory and data memory are often separate anyways. But there are limitations to these approaches. So some apps need this executable heap, and it also doesn't defend against return-oriented programming exploits, which we'll go to in a bit. And what you'll find is that these defenses are made, and then there's attacks based on these defenses. So that's why return-oriented programming you could think of as the second iteration of these types of attacks. And if you do want to test some of these stack execution vulnerabilities, you can actually disable the stack protections with this command with your compiler options, where you say -fno stack protector and so on. The first iteration of these return-oriented attacks was the return to libc attack. And this essentially enabled control hijacking without actually executing the code, so this makes that NX bit ineffective. So instead of having to generate a payload where you have to execute it on the stack, you can just overwrite the return addresses and have it return to different functions that are already available to you in libc. So for example, you can have the return address return to the exec function and then to /bin/sh to generate a reverse shell. And then the second iteration of these attacks was a bit more complex. This was the return-oriented programming, where you analyze the target code and you analyze how many return functions are being called in this code. And from here, you can essentially utilize the code that's just before these return addresses as what's called gadgets. So from here, you can analyze it and then generate shellcode that utilizes these instructions that are just before return addresses, and you can just keep returning to them. Although this is a much more complex attack to implement, there are tools that exist that will analyze your binary and generate gadgets for you. And in addition, they'll also tell you how feasible it is. So they'll analyze whether the binary is actually Turing complete, in the sense that it will allow you to program any type of code that you want to implement. Now, the other most common approach is randomization, and in particular, address space layout randomization maps shared libraries to random locations in process memory. And what this implies is that an attacker cannot deterministically craft an attack that will have them jump directly to an exec function. And this combats these return-oriented programming approaches. And currently, this is actually available on all major operating systems. So, this is a bit outdated, but Windows 7 had 8 bits of randomness for DLLs, and when they moved up to Windows 8, they had 24 bits of randomness on 64-bit processors. And then other randomization techniques do exist, such as syscall randomization, where you randomize the IDs of the syscalls, and then also instruction set randomization, where you randomize the ordering of the instructions. And there are ways to disable address space layout randomization if you do want to test some of these previous attacks, where you can essentially execute this command where you echo 0 to this function. So if you echo 0, it means that there will be no randomization and the address space will be static. If you echo 1, it will be conservative randomization, so that any shared libraries, stack, mmap, VDSOs, and heap are randomized, but everything else is static. And then echoing 2 will enable full randomization. And in addition to the elements listed in this previous point, that memory managed through this break function is also randomized. So this is just an example of how ALSR is implemented for example, for Windows systems. So this is just for one execution of a program. You have these DLL files that are loaded in memory at these particular addresses, and then on a second iteration, they would be loaded at different addresses. And you could see this reflecting when you execute some of your programs, and then you disassemble them. You will notice that there will be different addresses, and this can actually be reflected if we go back to our example of let's say we have our vulnerable code. If I just can open it here, of this format attack that we mentioned before, where you're taking in an argument in printf argv, and if we print out this %x that is a formatting attack on this, you can see that every time I do this, a different address will be printed every time, and this is due to this address space layout randomization. Now, everything in the process memory must be randomized. So this includes a stack, heap, shared libraries, as well as the base image. And this will prevent any of the aforementioned attacks that require this deterministic address space. Now, what about actually checking to see if there's actually stack buffer overflow? And this is where we come to the stack canary defense. And the reason why it's called stack canaries is because way back when coal miners actually used to use canaries, they would bring them with them into the coal mines to see if the oxygen levels were still okay. It's kind of morbid, but it was a technique used at the time to see that, okay, if we see the canaries dying, then that implies that we should get out of the mine. So in this case, we're using a small integer randomly chosen at the program start that we place in the stack before the stack return pointer. And most buffer overflows overwrite memory from lower to higher addresses. So in order to overwrite the return pointer, it would also need to overwrite the canary. So in this case, we're at the very least with this approach, we'd be ensuring that the stack canary would prevent the return pointer from being modified. And the value is checked to make sure that it has not changed before a routine uses the return pointer on the stack. And there are current commercial implementations of this, such as stack card. And you can see here a couple of examples where if we have this at the top of the stack, the canary might be placed at different locations on the stack, just before the return address could be modified. So there are multiple canary types. The first being the random canary, where we have a random string chosen at the program startup, and you would insert the canary into every stack frame. This is so that you would verify the canary before returning from every function, and you would exit the program if the canary has changed. And so this, although it still wouldn't prevent the buffer overflow, it would at least detect the buffer overflow, and it would turn any exploit into a denial of service. So, but to corrupt this, the attacker would have to learn some current random string, which is very unlikely it's very unlikely to predict. And then the other form of canary is called the terminary canary, where it's either zero or new line or a line of feed, and this is such that the string functions will not copy beyond this terminator. So the attackers cannot use the string functions to corrupt the stack. So anytime, so if we're trying to override a buffer and we have some format string, it would be capped by these terminator characters. So as I mentioned before, stack guard is one of the more commonly deployed implementations of these canaries, and it was actually implemented as a GCC patch and requires the program to be recompiled. And it has minimal performance effects. For example, in Apache servers, it causes 8% overhead. But again, they don't provide full protection. So some stack smashing attacks leave the canaries unchanged. In the case that it happens that the canary was unfortunately placed, and then heap-based attacks are still possible. So any overflows that are happening in a heap can still happen, as well as integer overflows. And for heap protection, there was a solution that came out where you can protect function pointers and set jump buffers by encrypting them using some XOR with some random cookie, but they're less effective and they do cause significant performance effects. And one assumption that these solutions are making is that you can actually recompile these your code, and often that's not the case. If you're using some third-party libraries that don't provide you with the source code, and you still have to integrate it into your code, then how would you protect it? So one solution was libsef, which focused on dynamically loaded libraries, and the key intuition here is that they would intercept calls to stir copy. So you'd intercept these vulnerable functions, and it would validate the sufficient space in the current stack frame. If so, if this property is true, then it does a stir copy. Otherwise, it terminates the application. So this was just an example of how you can provide a wrapper that makes the vulnerable functions safe. And then there's a whole bunch of other methods. So for example, stack shield. At the function prologue, it would copy the return address and the SFP to a safe location. And upon return, it would check that they're both equal to the copy. And this was implemented as an assembler file processor within GCC. And then another more popular method is control flow integrity. And there's been a lot of implementation of this in embedded systems where you combine static and dynamic checking. And essentially what you can show is that you can have a static determination of control flow and enforce the control flow integrity dynamically. So this worked by essentially adding some guards. So this is one example of how this was implemented was control flow guard that was implemented for Windows 10. That's a poor man's version of control flow integrity, and it would essentially protect indirect calls by checking against some bit mask of all valid function entry points in the executable. So for example, here you would have some guard check to ensure that the target is the entry point of a function, but again, it doesn't prevent an attacker from jumping to some valid wrong function. So there's many more advanced control flow attacks and defenses that have come out, and I highly recommend staying on top of the literature at these security conferences. So there's even more sophisticated attacks, such as heap spraying code injection, and more sophisticated defenses and version programming. At the end of the day, this is a cat and mouse game, as we've seen in the past with the non-executable stack being circumvented by the return-oriented programming. And it's always going to keep on going in the security space between attackers and defenders. And it's our job to continue the pursuit of perfect programming practices for perfect security. And with that, I'll conclude this section of the talk. There will be supplementary videos that will help out with the assignment, as well as a video explaining the assignment itself. And feel free to email me with any questions if anything was unclear. And I'd be happy to provide some of these code sources as well.